Okay, as Roman announced, I will speak about operator algebras of locally compact groups acting on trees. Recently, much of my thinking was focused on operator algebras and totally disconnected groups in more general. And in order to motivate this talk, I will give you some interesting questions about representation theory of groups acting on trees. So this is a so-called type 1 conjecture. And I guess the first thing I should do is introduce what a type 1 group is. G, a locally compact group, is type 1 if every factor representation is type 1 actually, or if every unitary representation yeah. It's only one. If it was two, then it was something else. If every unitary representation generates a type 1 for Neumann algebra. Okay, so there are several classical examples. On the one hand, we know that semi-simple Lie groups, they are type 1 groups. That's due to Hausdorff. And another class of more classical groups, these are reductive algebraic groups over non-Archimedean fields. That's due to Bernstein. So examples, classically, semi-simple Lie groups and reductive algebraic groups. Over non-Archimedean fields. Okay, what about other examples? Here's another candidate. T, a locally finite tree. Then out T just becomes a topological group, which is totally disconnected by declaring stabilizers of vertices open. They will be compact open since T is locally finite. And this is actually also type 1. This was due to Alchansky in the 70s. And at some point, the following more general conjecture came up. And as far as I could find out by now, it was originally due to Nebbia, Claudio Nebbia. But attribution seems to be a little bit unclear. So the following question makes sense, and I will motivate why it does. So T, a closed subgroup of out T, such that T acts transitively on the boundary of the tree. The boundary of the tree, I mean, you can easily, you can imagine that by fixing a vertex and looking at geodesics emerging from this vertex. And then the resulting set, just in the case of a free group, probably there you know this idea from the Cayley graph, is a nice compact topological space on which the group acts if it preserves the tree structure. So in this case, if G acts transitively on this boundary, then G is type 1. And this is the question. So why does this make sense? The boundary of the tree here replaces some classical structure that we have here, the boundaries of Lie groups or of reductive algebraic groups. So the representation theory of such a group should be in principle governed by a stabilizer of a point in this boundary. And this looks very much in structure similar to what we have for these classes of groups. I will come back to a reformulation and algebraic structure coming from this point of view. Okay. So my question is, can I, as an operator algebraist, contribute to this question? It is an intrinsically operator algebraic question, and up to now, there are only two classes of groups for which we know the answer. on the one hand, these are certain algebraic groups, for example, like PSL2QP. That's a group acting on a tree. That's a classical construction, and it actually acts transitively on the boundary. And here, the algebraic structure gives us the type 1 result. Groups like PSL2QP, and that's algebraic. And the other result is more of combinatorial nature. These are so-called Burger-Mozes groups, and that's combinatoric. Let me tell you what a Burger-Mozes group is. So I give myself a permutation group, and it acts just on the standard endpoint set. And I fix the n regular tree. Now I can consider the following picture. Take the n regular tree, and happens to be 3. And I give myself an element in T and a vertex of the tree. Okay, now I can define what the local action of the element G at V is. So let's say this is GV. Then I want to know what the local action is. In order to determine the local action, I should observe that the edges adjacent to V are sent to the edges adjacent to GV. So if I can make sense of some kind of permutation here, that will give me a good notion of local action. And the way to do that is to label the edges by numbers corresponding to the regularity of the tree, in such a way that around each vertex we have a bijection to the set 1 to n. So now, of course, I can explain what it means to have local action equal to a sigma in the permutation group sim n. It is just the unique permutation that corresponds to the permutation of labels. Okay? Okay, this is the local action. At V. So now, Burger-Mozes said BUF, the group of all automorphisms in T, which everywhere act locally like in F. Okay. And this has a natural index 2 subgroup. Or maybe I should write it a little bit differently. The group generated by edge stabilizers. That's a natural index. That's a natural subgroup in here, and this is abstractly simple. And it has index 2. If F is transitive and generated by point stabilizers. Okay, so now we found interesting groups acting on a tree. Interesting because they are abstractly simple. Abstractly means really just as a group. Any normal subgroup is easier, trivial, or everything. No closeness bedingung, no closeness condition. And it is big in the sense that it has index 2 in this huge universal group. So UF plus is an interesting candidate to study. And actually, these groups are type 1, if and only if F is too transitive. I will explain that.
So is F a subset or subgroup?
It's in the subset, subgroup, sorry. What?
Does it have to be a subgroup?
It will be automatically because you can compose locally. So it would only make sense to take F a subgroup.
I mean, the whole thing depends on how you identify those edges.
So you fix the labeling in the beginning, and then you define this with respect to fixed labeling, and it's a little observation that it doesn't depend on the choice of the labeling up to conjugation in the automorphism group of the tree. So if you have two labelings, there's a unique automorphism which sends one labeling to the other, and one chosen vertex to another chosen vertex that defines a unique automorphism, and this will conjugate the two ways to define it. As an abstract group, it's exactly uniquely defined. Where did I put the chalk? Thanks. Okay, so the question was, is UF a type 1 group? And one result which was in the literature, this is Aman, a PhD student in Zurich, and Giobotaru, who he wrote down the proof that UF plus is type 1. Oh, it should be a small type. If F is locally too transitive. So actually, this is exactly the case when you have acts transitively on the boundary. What is too transitive? Is too transitive. Okay. So, however, another question was open. Is the inverse true? Question. Actually, as she mentioned it, if F is primitive, whatever that means, it's a non-triviality assumption on permutation groups, but not too transitive. Is you have type 1 or not? So the general idea should be that it's not supposed to be type 1. And that's actually a result part of work in progress. The moment I'm writing down things with Cyril Oudayer. UF plus is not type 1 if F is not too transitive. Okay, and this is a special case of a more general result, because actually what we prove, the group for Neumann algebra of this group is not amenable. And hence already the left regular representation witnesses the failure of type 1. Okay, so this is actually one shadow of theorem which tries to cover by and by the whole non-to transitivity of groups acting on trees. These are groups which do not act locally too transitively, like around one vertex, they don't act too transitively. And in this generality, we can actually show that the group for Neumann algebra is non-amenable under some usual, non-triviality assumptions. One has to assume that the group acts minimally on the tree. This is something that I don't want to add because this is a little bit technical for people who never heard about it. But in the end, the aim of this project in several steps would be to really cover converse to the type 1 conjecture. If a group satisfying some non-triviality assumptions, linking the group to the action on the tree in a proper way, does not act transitively on the boundary and is not amenable, does it follow that the group for Neumann algebra is not amenable? And in some cases, we can prove that, actually. Since it's work in progress, I don't want to mention so much more on that. But I want to focus on some older work, which was inspired by the type 1 conjecture and goes about C-star simplicity. Okay. C-star simplicity. So a group, a locally compact group, G is called C-star simple if its reduced group C-star algebra is simple as a C-star algebra. If C-star reduced of G is simple. Okay. Since I'm speaking in front of a for Neumann algebraic audience, I guess I should recall quickly what the reduced group C-star algebra is. So G, locally compact for delta from G to r bigger than 0, the modular function. And fg in the continuous functions with compact support, then we can define two operations, f convolution g, this is the usual convolution product as we know it, and we can define an evolution by taking a correction and just taking the conjugate and precomposure with the inverse. And then the reduced group C-star algebra is the closure of this algebra in norm inside the bounded operators on L2 of G, on which it acts also by a convolution product. Okay? So the point here is that we cannot just simply take all the unitaries coming from the group and take a norm closure of the resulting span inside the operators of L2 of G, but we have to take this continuous algebra and take the closure of this one. That's the only point why I mentioned it. So C-star simplicity is studied for several reasons. And maybe the first one, historically, was examples of C-star algebras with interesting properties. I don't want to go into the history here. That was, for example, the reduced group C-star algebra of the free group on two generators that was Powers in 75, who showed that this is C-star simple. Then the next one is probably unitary representation theory. And here the keyword is weak containment. So let me just briefly mention that orally. Group is C star simple if and only if any representation, any unitary representation which is weakly contained in the left regular representation is already weakly equivalent. So now, without giving too much details what weakly contained means, it's a very rough relation on unitary representations. And it's, well, as for example, Fell wrote it in one article, determining the representation theory up to weak equivalence is the first step in understanding representations of a locally compact group. So in this case, this can be, from this point of view, one can see this as a motivation. And very recently, this is actually structure theory of groups themselves, of theory of groups, which became relevant mainly in the discrete setting at the moment. So as I mentioned, the discrete setting, let me put things a little bit into a context historically. I think you have to work in Germany for a few years in order to get it. Okay. So historically, the result of powers this was the first C star simplicity result. And that was for F2. Okay. So afterwards, a lot of combinatorial techniques based on Powers' results were dominating the field. I mean, people were showing that certain groups would be so-called Powers groups or modifications of that. In the 90s or end of the 80s, there was a short divergence from that ideas, implementing ideas more related to so-called property RD, more analytical in spirit. But the real turn came in 2014 with Kalanta Kennedy, who proved that G discrete is C star simple if and only if G acting on the so-called Furstenberg boundary is free, or topologically free, if you like. Their original result was actually topologically free. Okay, this gave a different twist to the whole story, because now we had a dynamical characterization of C star simplicity, and that triggered a whole development. This is very quick development. Since then, so for example, Breillat, Kalanta, Kennedy, Osawa, Le Boudec, and let me mention Kennedy and Horgerup. So Breillat, Kalanta, Kennedy, Osawa, they basically wrapped up the whole business of C star simplicity for discrete groups in one paper exploiting this new description and proving C-star simplicity for all groups which were known to be so before in a much simpler way, providing at the same time many new conditions. Le Boudec gave a counterexample to a very well-known conjectured description of C-star simplicity, which turned out to be false. See? Kennedy and Hogrup gave then finally the nice algebraic characterization of C-star simplicity. So this was what I mentioned with the structure theory of groups. However, all this is for discrete groups. What about locally compact groups? And this was a question by de la Have in 2007. Is there non-discrete C-star simple group? And first result in this direction that I could obtain in 2015 is the following. If G is C-star simple, then it is totally disconnected. Okay, so this puts the ball in the part of the field where I would like to play with totally disconnected groups. Okay. Let me right away give you a useful application of this theorem, although it's probably just an observation, but it links things back to my original motivation of type 1 groups. Corollary, a C-star simple group is not type 1. And as I said, this is more of an observation. Let me give you a short proof to show you how to do that. So first of all, let's assume G C-star simple and type 1. Okay, and we will deduce a contradiction. Simple. So first of all, we know type 1 groups which are discrete. These are just virtually abelian groups, and they will be hardly ever C-star simple. So we are in a non-discrete set. Further, since we are C-star simple, G is totally disconnected. Okay, G is totally disconnected and non-discrete. Okay. And further, G is also not compact. Because we just know Peter Weil theory. But now, there's only one simple type 1 C-star algebra which is not unitil. That's discreteness. And this is actually the compact operators on a Hilbert space. Okay? But now let's take normalized, I take the Haar measure on a totally disconnected group to be normalized on a compact open subgroup. I will just take this projection. This is a projection associated with compact open subgroup. So if I now compress, this is a result of how was your brother called, Alain? What? How was your doctor brother called again? with the Hecker algebras? What? Chanef, thank you, yeah, okay. This was the result, thank you. That was the result of Chanef, that if you compress the reduced group C-star algebra with such protection, then actually what you get is the so-called Hackett C-star algebra. And this is finite dimensional, obviously, because pk is a projection in the compact operators. But that cannot be, okay? And that finishes the proof. This is a very short consequence of these considerations. But it actually it gives the motivation in hindsight also for the C-star simplicity. And actually, I first was thinking about type 1 groups, and then C-star simplicity. Okay, but what about positive results? Are there, after all, non-discrete C-star simple groups? And yes, there are. Back to Burger-Mozes groups. If F in the symmetric group N is transitive, generated by point stabilizers, and there exist I and J such that the fixed groups in F of these I and J are the same, e.g. F is the isometries of a cube acting on the faces of the cube. Then UF plus is C-star simple. And this was another theorem of the same paper. Okay, so we indeed have examples of C-star simple groups which are non-discrete. Okay, how about the techniques to prove something like this? Actually, considering the time, I don't want to go too much into to how to prove that, but it's a result really for groups acting on a tree. And it exploits the fact that for such groups, a stabilizer at infinity is huge. It's an open subgroup. That's the point, basically, in the proof. And it's in stark contrast, of course, to the condition that we have for our type 1 conjecture, where we would act transitively, and the stabilizer is of a very different nature. Okay, so I was recently thinking about that, but I cannot say anything at the moment, nothing concrete. Yeah, I mean, I was having these things in mind, but at the moment I have other projects. Yeah. So, yes, yeah, I have 3 minutes, no? 45 or 40 minutes? Aha, I see, then, okay. Then I will not wipe the blackboard, but just tell you in a short words something else. Of course, these were simplicity results showing that certain groups are not type 1. I mentioned before a result using for Neumann Algebras showing that certain groups are not type 1 again. But now back to the original motivation. I mean, what about type 1 results? And there at the moment, the plan is to exploit the algebraic structure that I mentioned in the beginning. If a group acts transitively on the boundary of a tree, it has Iwasawa and polar decomposition, actually. Iwasawa decomposition means in particular that we have an amenable subgroup, the parabolic, so to say, which is co-compact. And another result that I meant to briefly explain is that if we have any locally compact group with a co-compact amenable closed subgroup, then the resulting C-star algebra is never C-star simple. And this is to be considered as the very first step in investigating this class of groups to slowly stack up pieces of puzzles to then complete to a proof from an operator algebraic starting point for this type 1 conjecture. So this is the end, and I wanted to briefly explain this strategy. But instead, I want to thank you for your attention and finish my talk. Mm-hmm. Yes, this is the generality of our result. In contrast to the question, we could even, I mean, any non-primitive group is not too locally, is not too transitive. I mean, too transitivity implies primitivity. So if you're not primitive, then this is in the scope of the theorem that I wrote down. This is really for the general class. It gives a dichotomy, really. I mean,
you actually, when you stated the theorem, you assumed it was not primitive.
No, not in the theorem. I mentioned the question, yes. The question asked for the, I mean, okay, maybe I failed to make this contrast clear. The question asked whether among primitive groups, the non-locally too transitive would give something non-type 1. And the point is that you can prove it just in generality without any primitivity assumption, because this is just for Neumann Algebras, and you use the flexibility that you gain from the setting. There's no algebraic, I mean, for this part at least, you wipe out completely the algebraic structure almost. Then that's a cute point about that work. I didn't mention one other example. I can get type 3 factors from, well, so-called Schlichting completions of Baum's-like solitary groups. I mean, basically they are HNN extensions of profinite groups. So you take, for example, set P, and I mean, the completions set P, and you take subgroups of finite English, just like you would do that for Baum's-like solitary groups, and you take the HNN extension of that. This is going to be C-star simple also. It acts on a tree in a natural way. It's just Basser's theory applies in exactly the same way. And the factor of that group is going to be type 3 with index 3 lambda for lambda equals, let's say, m over n absolute value, where m and n are the parameters that you would get from the Baum's-like solitary group. The Baum's-like solitary group has these two parameters, like, oh, someone has Japanese chalk? Okay. These two parameters. And then you get type 3 m over n, or, I mean, of course you have to order things correctly. Whenever that makes sense, otherwise it's, for example, if one of them is 1, then you get something solvable, that's okay. If this is 1, for example, then it doesn't work. I mean, if m and n are in absolute value the same, then this is not the case. But in all other cases, you get a type 3 factor. I didn't get such examples, but actually, I mean, it was known by work of Sutherland that you can get any type 3 lambda, but he didn't use totally disconnected groups. I mean, the group for Neumann Algebras of certain kind of build-up groups get any 3 lambda. But actually, that's something I should mention. Yue Suzuki, he recently also gave in a very cute construction, quite elementary, for other examples of C-star simple groups, and he also obtained a factoriality result where he can also, in a natural way, cover, like, let's say, rational lambda between 0, strictly between 0 and 1. That's the same. Thank you.